So in this video, we're going to see our first scheme for delegating quantum computations, which is maybe the more intuitive one. It's based on the idea of computing over encrypted data. So the main cryptographic ingredient that we're going to rely on is the quantum one-time pad that you discovered many weeks ago. So let's see how this works. So here's the setup. There's a circuit that the verifier wants the prover to run. So this is the circuit here that we want to execute, and we want this circuit to be executed on the 0 input. So everything that's drawn up here is in the control of the prover, and I'm going to write at the bottom things that are controlled by the verifier. So instead of having the prover run the circuit on the 0 input, we're going to have it run the circuit on an encryption of the 0 input. So what we do is that instead of telling the prover apply these zeros, the verifier applies a quantum one-time pad. So he generates random keys, A1, A2, A3, and B1, B2, B3 at random. He prepares the encrypted single qubit states that would lie here and sends these encrypted states one by one to the prover. So here we require the ability for the verifier to prepare single qubit states in the computational or Hadamard basis. So now the prover has all these qubits, he's running the circuit. You could worry that the circuit here has to be told to the prover, but in fact you could use a universal circuit and hide the computation in the input. So let's not worry about this now. Let's imagine that the prover knows the circuit, we want it to execute the circuit. Here's how we're going to do it. So when an X gate is supposed to be executed by the prover, we actually don't need to do anything because this X gate here anti-commutes with the Z here, depending on the value of B2. But anyways, this anti-commutation will just be a global phase plus or minus 1 that we can ignore from the purposes of the computation. And then it'll result in changing this A2 to A2 plus 1. So in order to go from the state before the X to the state after the X, the only operation that has to be performed is that the verifier should update the bit A2 to A2 plus 1. And that's the only thing that's equivalent to applying the X. For Z, we have a similar situation. The only thing the verifier needs to do is update B2 to B2 plus 1, and the prover doesn't have to do anything. C0 gate, same thing. The update rule is a little bit more complicated. It involves the bits A1, B1, A3, and B3. And I'm not going to tell you what it is now. I'll let you figure it out as an exercise, but you can just write the C0 gate and see how these bits should be updated. Now we've done X, we've done Z, we've done C0. How many gates do we have to cover? Well, we need our universal set of gates for quantum computation. It turns out that here is a universal set. We could take the X gate, the C0 gate, and we need two more, the Hadamard gate and the T gate. Hadamard gate you've seen before. The T gate, what it does is that if the input state is a qubit in the state 0, it does nothing. And if it's a 1, it adds a phase of e to the I pi over 4. So that's the T gate here. So the Hadamard gate turns out is a little bit complicated. I'm not going to explain it directly. We'll come back to it a little later. The T gate also requires some work. Unfortunately, we don't know how to implement the T gate simply by updating these keys. In fact, it's impossible because of the fact that we're introducing these e to the I pi over 4 phase here, and X and Z, they just have plus minus 1 phases. So there is a way to implement the T gate, but it's a bit more complicated. We'll see it in the next video. It involves the verifier preparing what's called a magic state. So that's a special state that's prepared in one of two possible states, and it's sent over to the prover, call it phi, who is going to use this state, combine it with the qubit on which the T gate should be applied, perform a measurement, report the outcome of the measurement to the verifier. The verifier will give another bit C prime to the prover, who will use it to perform some correction and proceed with the computation. The verifier will also update his key bits B, A2 and B2 to some values depending on the C and the C prime here. There's a little bit of a slightly complicated protocol, but it can be done, and the upshot is that The amount of work that the verifier has to perform is similar to the amount of work that has to be performed for the other gates, plus preparing this single qubit magic state here. But then, once we know how to do this, we can go through the whole circuit in this way, and what happens is that at the end of the circuit now, instead of having the state circuit applied to 0, in my case this is a 3-qubit circuit, this is what we'd like to want and then to have, and then we'd ask the prover to measure the output qubit, report the outcome to us. Instead of having this, then we'll have this with the Pauli correction that we've kept track of. So x to the a, z to the b, let me call them b prime and a prime. These are the new values of a and b that have been updated by the verifier throughout the computation. But taking those into account, the z will not matter if we measure in the computational basis, and the x to the a prime we can take into account if the prover reports a 1 and a prime on that output qubit is a 1, then we'll know that we have to flip the prover's answer in order to interpret it as the real answer that the circuit would have given on the input qubit 0. So that's almost all the protocol. There's a little bit more coming, but you can already see that this protocol does not leak any information to the prover. Why? Simply because all the information that's being sent to the prover is always completely random. The input state here, by the property of the quantum one-time pad, just looks like a fully mixed reduced density matrix. These updates don't involve anything sent to the prover, so there's no risk here, no risk here. The only risk would be when we apply the T-gate. That requires the magic states, but again, these don't leak any information to the prover, no information about the computation. And then you could worry about these bits C prime that I haven't told you about. We'll see these in the next video, but I can promise you now that these bits are uniformly random. So all the information the prover gets just looks completely random to him. He's not learning anything about what's going on, so the protocol is blind. Then there's a question of whether this protocol is verifiable. What if the prover doesn't perform the actions that I'm telling it to do? What if when it's supposed to implement this T-gate, it does something different, it makes a different measurement than the one it's supposed to perform, obtains a certain outcome, doesn't report to me the correct value of C? How am I going to detect that? So there's 2 steps in order to understand the kind of attacks that are possible for the adversary, where by adversary I just mean malicious prover. So the first step is the reduction from general attacks to Pauli attacks. So what's a general attack of the prover? What we can always imagine is that this prover always does the correct thing, which is apply the gate that it's supposed to apply in the circuit, followed by some deviating unitary, some kind of operation that it's not supposed to be doing. So let's call it U1. And then it applies the second gate correctly, but then it does something crazy, U2, etc. All the way until the end of the protocol and the U1. And I can assume that these deviations that are performed by the prover are unitary by delaying any measurement that the prover was going to perform until the end of the protocol. So that's what a general attack looks like. And because all these are unitary operations, I can rewrite this in a different way. I can actually rewrite this as an arbitrary unitary U followed by the exact circuit that was supposed to be executed, Cm down up to C1. Right? The way I did this is simply by commuting the U's and changing their values. You can think that this last U that I wrote here basically undoes the whole circuit and then applies this unitary that was the real deviating attack. So there's always going to be, because these operations are unitary, there's always going to be a way to rewrite the general attack as don't do anything, do the real thing until almost the end, and then at the end, before all the final measurements are performed, apply some arbitrary unitary that undoes everything that you've done and does something malicious that you wish you'd be doing. Okay, so any attack can be put in this form. Now the second step, important, is to use the properties of the quantum one-time pad to argue that in fact a general attack that implements a general unitary is equivalent to simply applying an arbitrary Pauli operator on all the qubits at the end of the computation. This is a trick called the Pauli twirl. It's a computation that you have to make. So what does this attack U look like? It takes as input some state rho, which is the state at the start of the protocol. And what are we doing overall? Well, there's the one-time pad that the verifier is applying, and this corresponds to applying a random Pauli, Q, to the density rho. So that's the one-time pad. Then the circuit is executed, C dagger. Then the prover's attack U is performed, U and U dagger. And finally, the correction that the verifier performs at the end of the protocol is applied. So this is another Pauli operator, call it Q tilde, that's executed at the end of the protocol, and this Q tilde is chosen so that the identity CQ equals Q tilde C holds. Right? The point of Q tilde is to undo the quantum one-time pad after having been updated as the execution of the circuit was going through. So Q tilde is chosen so that this identity holds, which means that this expression here I can rewrite as the sum over all Q tildes now of Q tilde U Q tilde C rho C dagger and then the daggers. So U dagger Q tilde U dagger Q tilde. And so this operation here of conjugating the U by random Paulis here and here, here and here, this is called the Pauli twirl. And if you expand U in the Pauli basis, you can rewrite this expression as a sum over Pauli's P of Q tilde, the sum over Q tilde is still there, some coefficient alpha P, which is non-negative, Q tilde P Q tilde, the circuit, and then again Q tilde P Q tilde. So this is an equality that you have to verify, but you verify it by expanding a unitary U in the Pauli basis and seeing what happens. And basically what this means is that these non-negative coefficients, they're like a convex combination, and so we're just saying that an arbitrary attack of the prover due to the use of the quantum one-time pad reduces to a convex combination of Pauli attacks. That's great because now we only have to understand what the effect of Pauli attacks is. That's the last step of the security proof. Let's look at it. Alright, so what does a Pauli attack look like? This is again our execution of the circuit, and the Pauli attack is something that's going to be performed at the end of the protocol here, where the prover would apply any Pauli that he wants, P1, P2, P3 on the qubits. And our goal is to detect such a malicious attack of the prover. And the idea is going to be a very neat idea. It's going to be to introduce test runs. So there's going to be two types of test runs, the computational basis test run and the Hadamard basis test run. And what's going to happen in these test runs is that the circuit that the verifier wants to be applied is going to be replaced by the identity circuit, doesn't do anything, without the prover noticing. So how do we do such a thing? Well, let's recall how we're having the prover execute the circuit in the first place. So in order to perform an X gate, we actually didn't say anything to the prover, we updated the keys. So if we want the X gate not to be applied, we don't update our keys, but the prover is not going to notice because anyways it wasn't told that an X gate was applied. So this is easy to get rid of, this is easy to get rid of, this is easy to get rid of. The T gate is a little bit more subtle because you have to know exactly how the T gate is implemented. But let me just promise to you that similarly, there's a way to change how the T gate is applied by providing a different magic state than the one that should have produced to implement the T gate, but in a way that the prover can't notice, so that even though it's thinking it's applying a T gate, actually it just applies the identity gate. Now, this is for these gates. There's also the Hadamard. I promised you we would return to the Hadamard. The Hadamard is a bit more subtle. You can't just get rid of it, and it has the effect of switching a 0 to a plus, a 1 to a minus. This is why we're going to have runs in the computational basis and in the Hadamard basis. And these H gates are going to be applied, but we'll think of them as switching between one identity circuit kind of test run to the other identity circuit kind of test run. So that's how we'll handle the H gates. Putting these aside, let's imagine a circuit without any Hadamard gates. What's going on here? The prover is doing exactly what it was doing in the case where we were running the computation, but now we're applying the identity circuit. Because the prover doesn't notice, if he was or she was to apply a Pauli attack at the end, it also applies the Pauli attack at the end in the case where this is a computation test run. But in a computation test run, we know exactly what the output should be. It's just zeros encoded with these Pauli keys. And the prover is going to report to us an outcome, and we can check, is this outcome correct or not? For instance, if the output qubit was the first qubit, then the outcome should be 0 if A1 was 0 and 1 if A1 was 1. This is something that we can check. And if the prover is indeed applying a Pauli here that's non-trivial in the X basis, then we're going to detect it. So that's the rough idea. Let me recap how this protocol works and how the proof of blindness and verifiability goes about. So first, we use the idea of computing on encrypted data. The verifier encodes the input using the quantum one-time pad, sends that to the prover. Because of the one-time pad, the input looks completely mixed, the prover has no information, and then we're going to guide this prover through the application of each gate in the circuit by telling it to apply the gate and updating the encryption keys of the one-time pad as we progress through the circuit. This is straightforward for most of the gates in our universal gate set, except for the T-gate. The T-gate requires a little bit more complicated interaction that we'll explain in the next video. Now, in order to ensure that we could verify that the prover is applying the circuit that it's supposed to apply, we had to introduce these computation run, test run in the X basis and test run in the Z basis. And in these test runs, what we do is that we exactly control what's going on. We apply the identity circuit without the prover noticing that we're applying the identity circuit. This enables us to check that the outcome of the computation is the correct outcome. Now, the last piece in putting the analysis together is to argue that this prover cannot distinguish which type of run is being performed. And I kind of told you that this was the case before. In practice, there's a very neat way to analyze the protocol to show that the prover cannot make a difference. In order to make all these arguments about, the bits sent by the verifier are random and the prover only sees the totally mixed state, a precise way to formulate this argument is to consider a different variant of the protocol, which is an entanglement-based variant of the protocol. So that's an idea that's familiar, similar idea that we saw in the analysis of quantum key distribution. It is possible to reformulate that protocol that I described to you as a protocol in which at every step the only thing that the verifier ever sends to the prover is half of an EPR pair. That's all. The verifier prepares EPR pairs and sends halves to the prover. And the protocol goes on like this until the end, and only at the end does the verifier measure some of its qubits, and depending on the outcomes, decides whether this was a computational run or a test run in the Hadamard basis or a test run in the computational basis, and uses some of the outcomes also to update the keys from the one-time pad. But now, because all of this is done at the end of the protocol, for sure the prover cannot make any difference between what is going on in any of these test runs. And so this way we get verifiability for the protocol. So that was our first protocol for delegating computation. It requires a little bit of quantum abilities of the verifier, preparing single qubit states in the computational Hadamard basis and also the magic states. But that's it. Other than that, it's a very efficient protocol. There's a little bit of communication that's required for every gate in the circuit, so it's an interactive protocol. Basically as many rounds as much communication as the size of the circuit.